The fastest baseball pitch ever thrown reached over 170 kilometers an hour. That's impressive, but even that record-breaking fastball would never be able to pass through a solid brick wall. It's just not possible. That is, unless we're playing quantum baseball. With a baseball, there are only two ways to get to the other side of a wall. One is to go around, the other is to burst right through. A thrown baseball might have enough energy to rip through a piece of paper, but even the fastest pitch would just bounce off a brick wall. But sometimes, quantum particles are caught passing through barriers they don't seem to have enough energy to break through. Logically, they should just bounce off, and yet there they are, sitting quite happily on the other side. How can that be possible? We call this quantum tunneling, and it only works because particles can act like waves. Remember Heisenberg's uncertainty principle? If we know a particle's energy or momentum, then we can't be certain about its position. There's a small probability, maybe 1 in a trillion, that the particle's position could be on the other side of a barrier when we thought it was over here. It didn't have to punch through. It took advantage of the uncertainty built into quantum mechanics to boldly assert that it was on the other side all along. You might be asking yourself, what relevance could this rare, obscure quantum phenomenon have in real life? It turns out that without quantum tunneling, none of us would even exist. Consider the sun. The sun shines because of nuclear fusion. Hydrogen atoms are fused together into helium atoms, releasing energy as light. One step in this process requires two protons to be pushed together close enough to form a nuclear bond. But protons are positively charged. They repel each other like magnets. Early calculations proved that overcoming that repulsion shouldn't be possible, even in the hot, dense core of a star. But it happens anyway because of quantum tunneling. It's still rare. It happens in less than 1 in a trillion encounters. But in those cases, the strong nuclear force can take over and allow those protons to bind. Without quantum tunneling, the sun wouldn't be able to shine at all. We also encounter quantum tunneling much closer to home in our technology. It's a key aspect of how flash memory works, for example. It also has its downsides. If we make a microchip too small, the tendency of electrons to tunnel will mean they wander all over the chip, even if we'd rather they stay on one side. One of the coolest applications of quantum tunneling is the scanning tunneling microscope, which allows us to see individual atoms. It works by applying a voltage to a scanner and to the sample it's examining, and passing the scanner's metal tip very close to the sample, but not quite touching it. Under classical non-quantum rules, electrons can't pass through the gap. But because of quantum tunneling, some electrons sneak through, completing the circuit. Tiny bumps on the sample reduce and lengthen the gap just slightly, increasing or decreasing the level of current, so the microscope can record the shape of the surface. With this, we can map DNA strands, or even build new materials atom by atom.
Empty space is actually roiling with activity. These are the quantum vacuum fluctuations. And every once in a while, those quantum vacuum fluctuations might be able to rearrange themselves in such a way through the process of quantum tunneling that it causes empty space itself to transition from the state that we see around us to something else. And that something else is something we don't quite understand. And one of the tools that we hope to use to uncover the properties of this transition is to try and simulate it in the laboratory. The goal of performing these experiments that are meant to model this process of, empty space undergoing quantum tunneling is to elucidate the exact dynamics of how it occurs. And it would be quite dramatic because you would form these pockets inside of which the laws of physics might be completely different, that then expand at the speed of light and effectively eat up all of space. I don't spend a lot of nights awake wondering if the vacuum is about to decay on me. The universe is quite old. It's 14 billion years. It hasn't happened yet, so it's probably not going to happen anytime soon.
Quantum tunneling is one of the weirdest and most useful features of quantum physics. It makes the sun shine, and it lets us build incredibly powerful microscopes and electronics. It may even be the key to the fate of our universe, but it won't make you better at baseball.